All right, welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell. You'll get notifications for this series and a bunch of others. This is the last video in the series, Multivariable Calculus, Chapter 3. We're in Vector Calculus. 3.9 is the Divergence Theorem. What we're going to do specifically is the Divergence Theorem and an example. Singular. And example. That's the sentence fragment now. Me fail English, that's impossible. Math, we do math. All right, our last main result of this course in this series, Multivariable Calculus. The crescendo is essentially the divergence theorem. Let E now be a simple solid region. What do we mean by simple? They just sneak these in there, but for us it's going to be the type 1, type 2, type 3 regions, solid regions that we discussed when we discussed doing triple integrals over solid regions. I'm hoping if we're going to use this, it would be something that I knew how to and trained you to how to compute triple integrals earlier. Remember, divergence is the dot product of the del operator in your gradient or your vector field, which says that that's going to be a scalar or a number, and then we have a triple integral of that scalar. So what divergence theorem tells us is if I have a simple solid region over in R, bounded by a surface which has a positive orientation, or outwards always, and if we have a vector field which has continuous partial derivatives, so we can talk about them in its divergence, we have that the surface integral over that vector field is actually equal to a triple integral of its divergence. And thus it's called the divergence theorem in English. A German mathematician, Carl Friedrich Gauss, and a Russian mathematician, Mikhail Ostrogradsky, independently derived these in the 1800s. And so in Germany, it's usually called Gauss's theorem, and in Russia, it's usually called Ostrogadsky's theorem. And in English, we can't pronounce Gauss or Ostrogadsky, so we call it divergence theorem. Let's do an example. From the previous video, we did this example already once. We used Stokes' theorem to compute the flux across this. What we're now going to do is use the divergence theorem to, instead of having to compute that horrible thing that we had to compute all the flux, all the things we need to compute the flux, we're now just going to use the triple integral over the solid region E. Then the picture, you have to also, which one is this? Is this the surface? This is the shell. An egg is the surface. Everything inside, the yolk and all of that, and the white is the ball. So when we say the unit ball or the unit sphere is the shell, just the boundary, equals 1. Our region E, our solid region E, is the unit ball, which is what? X squared plus y squared plus z squared, and it's not an equality, it's an inequality. Any ordered pair in space where they're less than or equal to 1 is everything inside there. Now that's everything inside the sphere also. That's the unit ball. The boundary of the unit ball is the unit sphere. So what they're saying is they want us to do the same thing. Calculate the flux coming off of the unit sphere, the boundary of this unit ball. And how am I going to do that? Divergence theorem says that the flux off of this sphere, or the flux of my field over the surface of the sphere, will equal the triple integral of the divergence over the unit ball. And that's how I'm going to phrase it. And then I don't have to do any of this calculating the parameterization or anything. I'm just going to find the bounds for my region, which is this simple region in space, and then compute the triple integral that way. Therefore, positively orientated, my boundary is S, which is x squared plus y squared plus z squared equals 1. And specifically in spherical notation, my bounds are going to be rho is between 0 and 1, theta is between 0 and 2 pi, and phi is between 0 and pi. What is that saying if you can't see it still? What divergence theorem says is the surface integral of my vector field dot ds is equal to, by divergence, the triple integral over my region E of the divergence of f dv. And then we don't have to compute any of that parameterization business. We're just going to find out what the divergence of f is, which is a scalar, and then we're going to find the bounds for our region, which we just did, and then we're going to compute. Therefore, what do I need? I need div f. The divergence of f, remember, is del dot f, which if you can't remember, del is the partial with respect to x, the partial with respect to y, the partial with respect to z in coordinates, dot product with p, q, r, or in our specific case, what are those PQR? PQR are Z, Y, X. And that's going to give me what? The partial with respect to X of Z is 0 plus the partial with respect to Y of Y is 1 plus the partial of Z with respect to X is 0. So I get 1. Oh, yay, it's going to create volume because our divergence was 1, so we're going to put a 1 in there. That's coincidental. That won't happen for you on your exam, I guarantee. Putting that all together now, what do I have? The flux of my field across the surface S ds is equal to, by divergence theorem, the triple integral of the divergence of f dv over my solid region E. My solid region E is the unit ball, which has these bounds. What that tells me is, and this was the triple integral E of 1 dv. And so some unknown book says this is the volume of this unit ball. So what is that going to be? 4/3 pi r cubed, and the r is 1, so 4 pi over 3. Okay, but let's practice doing triple integrals because we need some practice. This is now, what are our spherical Jacobian? Remember, this is why it's like, yeah, maybe try to remember all those things. I'm going to go from 0 to pi, the integral from 0 to 2 pi, the integral from 0 to 1 of now what? dv is rho squared sine phi d rho d theta d phi. And it helps you do this instead of just saying, oh, it's the volume of a sphere. Now what do I do? That's going to give me, I can separate all of these. This is the integral from 0 to pi of sine phi d phi times the integral from 0 to 2 pi of d theta times the integral from 0 to 1 of rho squared d rho. That is now equal to, what am I going to get? Negative cos phi evaluated from 0 to pi, theta evaluated from 0 to 2 pi, and 1/3 rho, not beta, I said rho. My brain has other plans. From 0 to 1, evaluated from 0 to 1, which is equal to, now what am I going to get? Careful, negative is going to give me 2 times 2 pi times 1/3, or, yes, the book is correct, the volume of the sphere with radius 1, or the ball with radius 1, is 4 pi over 3. Please subscribe right here, hit the notification bell. I'll see you in one of our other series.